My goal is to say a couple simple things. What I want to do is I want to talk a little bit about NLTS, which was a conjecture that was proven by myself along with Anurag, Anshu, and Nico Breuckmann, which is related to error correction, and talk about how its scope and where do you go from there, and then how do we make our way towards quantum probabilistically checkable proofs. The cartoon is sort of because one might naively think that it's like the NLTS is a necessary condition for quantum PCPs, but it's not at all obvious to me, like, what do you do once you have proven this result in complexity theory to make the step towards quantum PCPs? So I'll try to tell you a few of the things that I've been thinking about possible directions. None of the things I'll say are, published or, written down exactly, but they're just sort of intuitions as to maybe where the right steps are. Okay, so to begin with, and we'll get to the connections to error correction in a bit, but the simple idea is that calculating ground energy of Hamiltonian systems is a hard problem. So just to recap, what you can think about is you can think of like an array of qubits, or you can think about a general set of qubits which just have some interactions that are local. Here I'm going to use the word local in the way that computer scientists use it, meaning that each interaction only acts on a constant number of particles. So you could imagine they look like this, or maybe they're going across the grid or whatnot, but they're just defined by some local interactions. And there's a matrix, it's a 2 to the k by 2 to the k matrix, which is the local Hamiltonian term that describes the interaction. And given a local Hamiltonian interaction, you can always think of that local interaction as a global interaction that is acting trivially on the other n minus k of the particles. So, and the way you mathematically do this is you say, okay, well, the interaction is just represented by this 2 to the n by 2 to the n matrix, and it's just a matrix with a very simple tensor product structure. Okay, so that's how you take each local Hamiltonian term. And once you add up all the local interactions obeying the tensor product structure, you get what we might call the Hamiltonian that describes the whole interaction. And now this Hamiltonian is a very complex matrix. A 2 to the n by 2 to the n matrix, but it's not all possible 2 to the n by 2 to the n matrix. In particular, it had this structure, right? It came from this very structured thing, so it's a strict subset of them. For one, it's a sparse matrix, right? And what's the computational problem you might be interested in with this Hamiltonian? It's to sort of calculate what the low energy states are, or even, first of all, is to just calculate what the lowest energy might be. And the energy of a state, right, is just the eigenvalue. It's just the quadratic form with the Hamiltonian tossed in the middle. Okay, well, we're a little out of luck that calculating the value exactly, or even to some inverse polynomial additive precision, that problem is QMA hard. This was proven by Kitaev in 1999, so over a century ago, so to speak. So, okay, we're not going to be able to do that. But maybe we don't need this kind of precision. Maybe we just want to calculate it in some approximate nature. So we could ask, how hard is it to approximate? So what we have is there's some real minimum eigenvalue, some lambda min, and we know it's QMA complete to figure out anything with some inverse poly precision. But what if we asked some constant precision? It's like 1% off, whatever that lambda minimum is. The lambda min was like 5% times n, maybe trying to estimate 6% times n. Well, it turns out that is NP hard. So it's classically intractable just for the classical Hamiltonians you can write down. So you're not going to exactly be able to do that. But how does it compare to this QMA hardness? How does it compare to like generic quantum computations? Is there a separation between the set of problems where they have classical hardness and where we have quantum hardness? It might be that a quantum non-deterministic computation can actually calculate this sort of energy. Well, there's this conjecture called the quantum PCP conjecture, which precisely says that we believe that even this approximate estimation should be hard for non-deterministic quantum computation. It's just a conjecture. And the big evidence towards it is that the classical result exists, and we sort of believe that there's some natural parallels there. Okay, but how do we go about like trying to make progress on this conjecture? And to do that, I need to introduce a simple notion, which has gained a lot of popularity recently, called state complexity. And so to do that, you just need to first understand that the vast pantheon of classical computer science was based on the notion of something called decision complexity, which is given the description of a problem, just answer in binary, just answer yes or no. And that could be something as simple as, does some circuit or some quantum computation, does it have any accepting quantum states? That's a yes/no question, just does it accept or does it not? But then you could also ask, is there a state version of the question, which is to actually output the quantum state that matches the description. And the analog here is that it's just the accepting quantum state. So it's a problem where you sort of give it a classical description and the output is a quantum state. Okay, what does this have to do with the quantum PCP conjecture? Well, you could also define a class which may be called state NP, which is the set of classical descriptions of states. Now, classically describing a state, we have to give ourselves some nuances here. And what I'm going to say it is a set of strings for which given the representation, given the string xn, you can efficiently calculate trace of some local observable with some actual state. So in some sense, this classical string encodes all the local measurements outcomes. Does that make sense? So it's not saying, it doesn't really write down the whole state because it's a succinct sort of representation, but given this representation, it's enough to calculate the local observable outcomes. So here's some examples. One you can do is you can tell me the description of a constant depth quantum circuit. So I just give you a circuit and I say, look, if you'd run this circuit on your quantum computer, at the end of the day, there's going to be some state sitting on the computer. And then this circuit is describing that state. It's the recipe for the output, right? And given this description, you can actually calculate this trace of O psi n for any state. Another option could be like a description of what's called a matrix product state, right? Or another sort of a third option that you might say is like listing the stabilizers for a stabilizer state. So this is a sort of a different notion of how to describe a quantum state by describing what are some operators, some unitaries that preserve this state. Maybe I should also tell you some non-examples for state complexity. And so one could be just a list claiming to describe a map. It just says, oh, for some observable, oh, here's the answer. I just list out all the possible things. There's only polynomially many that form a basis, so you just list them all. The problem with this is that there's no way to tell if there really did exist an honest state that corresponded to all these measurements, right? Just telling you what the answers are without sort of giving you a description, it makes it hard. All the examples on the left, there's sort of a proof, right? That the measurements that you get out corresponded to a state. That's the real crucial part of them. And a second one could be like a classical shadow of a quantum state. It's hard to tell if the classical shadows actually corresponded to a real state, if someone gives you a purported list of them. Okay, so state NP is just a set of objects which can be classically described, but once you have this classical description, all the local properties are already encoded in this classical description. So why talk about this?
Can I ask a question?
Yes.
To clarify
absolutely.
What you had before. So if you have that list and you're producing the state, you're still allowing some kind of quantum operation to get that value, right?
To calculate the value?
Calculate the trace, right?
No. So I'm just saying you can classically even calculate the value from this string. I should have clarified that. Yeah.
Yeah, because it's local if you only involve a local piece. But you want that function trace over Cn to be classically.
Yeah, given x, you can calculate. Given x and O, you can calculate this.
But you also know there's a state where it does.
Yes, right. So it's for real states. Yeah, Toby.
In the definition, so what's ruling out non-examples
then? Well, yes. Implicitly, there exists some state psi. That's just what it means. Is really that there exists. Maybe I should have written as there exists a state psi n that this corresponds to, right? That there's some honest state. I don't have to say what the state is. And a priori, actually, the set of observables don't have to correspond to the same state. Like, for example, the state could have been the cat state with a positive sign and the cat state with a negative sign. The fact of the matter is all their local measurements are identical. So the set of these representations, it doesn't matter, right? So it doesn't have to be a unique state. It just has to be the existence of some state.
Question.
Yeah.
Are you assuming there's a family of quantum system, or you're fixing one quantum system?
Yeah, let's just, you can really formally want to say it's like a parametrization over n. So for every system size, you have something. But that's a little too technical for 410, Let's go even simpler. Yeah, Robin?
What's the connection with NP? Why is it called state NP?
Because it's a classical witness that gives you the answer. So like you could imagine, I should have really written in the purple box that you can use to classically calculate this trace. Right? Like everything is done classical. Just as a classical representation of the state, you can answer all these local questions classically. You could call it state QCMA if you wanted to say, given a classical description and a quantum computer, you can calculate all these things. Okay, yeah. So where does this come in? Well, let's imagine there was a state NP object of energy below this conjectured threshold, right? What does that mean? It means that there is some quantum state which which has this classical description, and it's a very good approximation. Its approximation is below this epsilon prime. Okay, well, if this state existed, then what you get is that this quantum complexity class QMA, it will collapse to the class NP. So it says that there's no computational power on quantum non-deterministic computation. So it says if this QMA conjecture is true and this state NP exists, then non-deterministic quantum computation has no more power than classical non-deterministic computation. And the reason is because this state sort of serves as an entire witness. All the complexity of showing that an approximation exists can all be done classically. You didn't need your quantum computer at all. Put that away. Just do it on your laptop, right? Okay. So what we really believe is that if this conjecture is true, since we don't believe this at all, that there shouldn't exist state NP objects. So one way to say this is that the quantum PCP conjecture necessitates some notion of state complexity lower bounds. And really, you could actually do this even more generally. You can say that quantum PCP plus any sort of complexity class conjecture like QCMA or not equal to QMA or whatever other thing, it generates some notion of some state C lower bound. So I'm not going to say what that could look like for all the other things, but it really implies these sort of state complexity lower bounds. And one way to look at this is now it's saying, okay, well, I had a vastly complicated problem about embedding computation in Hamiltonian systems and trying to understand all these things. And let's just make it even simpler. Let's throw away all the notions of computation and let's just talk about the entanglement complexity that is inherent, the verifiable entanglement complexity. And let's see if any of those statements are true. Because if those statements are at least were false, then we can pack up and go home. It's just much, much easier. Okay. So the key idea is that when we look at just the state NP lower bounds, we get the following lower bounds are implied. Specifically, that there exists local Hamiltonian systems for which all the low energy states below some epsilon threshold. So think of epsilon here as like some number, like 1%, 100%, doesn't really matter, that they require some large circuit depth. This is just one of the state NP lower bound consequences you can derive. But the quantum PCP conjecture is going to imply all the state NP lower bounds, but let's just focus on this one. Okay, so this we were able to prove last year. I should say that this conjecture, this NLTS conjecture, was first posited by Friedman and Hastings, who had given talks in the earlier part of this program, and we showed that there exists some Hamiltonian systems so that every low energy state requires at least log circuit depth. Yeah.
What do we know about the other state NP lower bounds that would be employed by that? Like,
right. So you can go through this and just replace this log circuit depth with whatever is your favorite thing. So you could talk about stabilizer states. You could talk about states with stabilizer states with low T gates, with few T gates. And simultaneously, actually, you should be able to say the and of all these statements. That you should be able to, all the classical ways that you can describe it are insufficient. The reason I say this about the stabilizer and T gates actually is that Nolan and his co-authors have a very nice poster outside about that, which I recommend checking.
And
So-
it's true in that case.
Yeah. The and of this circuit depth plus the stabilizer gates with low T count, they have the and. Later in the talk, I'll talk about some sort of series computation, which is not known, which is also necessary. But yeah.
So you prove a much stronger result. You take up one of the log. Why do you have two log?
Okay, so two logs come from roughly one is that if you have a log circuit depth, then the light cones of any one particular things there's one log off. And then the other log is going to come from like information spread. We'll see why you have these two logs and where we can get one log. But I think that's not the right message to be focusing on. Yeah. Any other question? Okay. So this was actually after a sequence of partial results, trying to like make progress. And what did all these results do? We started chipping away at proving lower bounds for larger and larger sets of states. Right. In the end, what we want to do is we want to prove lower bounds for every low energy state. So what we did is like sequentially there was a chipping away, and eventually we proved it for all the states. And it's based on error correction. That's sort of how we tie into the rest of this program, especially the codes that were described in much detail in Pavel's talk at the beginning of today. So I won't say much about like how the codes are constructed, just sort of, I'm going to try to extract all the properties of the codes that we need. Okay. So why circuit depth? So there's a simple perspective you can take on circuit depth, which is that if you have a quantum state and it's described by a circuit of depth that's doubly logarithmic, then it's trivial in the sense that anything you want to do with it, classical computation. This is the state NP region, the green region. The yellow region is where those are the states which my quantum computer can sort of express and sort of play around with. But my classical computer, we don't think can. And then the red region is just like all hope is lost. Neither quantum or classical can do anything about. So what we want to do is we want to break out of the classical. We want to break out of the state NP perspective, right? Okay. So before I get to like sort of a little bit about how we solve an NLTS, let me talk about what we should be looking for next. So I think there's two directions one could take. One is we might want to prove some stronger state complexity bounds. So there's been some recent work on this area, which is to construct local Hamiltonians for which they're even stronger lower bounds. So this could be proved for more of the state NP lower bounds we might want to prove, or it could be about other sorts of classical descriptions. And I'll talk about both of these in due course. The other is the direction I think is more interesting, which is we should try to reintroduce computational hardness. So remember, we went to these state NP lower bounds because they were easier and they extracted all the computational hardness from the problem. But now we should try to put that back in and see if we can get anything. So we want to prove that these Hamiltonians, this quantum PCP, they're at least MA hard or BQP hard or BPP hard, or construct local Hamiltonians which are simultaneously NLTS and NP hard. We'll talk about all of these in due course. Okay, so in order to do that, let me say a little bit about how you might prove the NLTS result and where the complex entanglement is coming from. So in order to do this, we first need to prove a way of proving circuit depth lower bounds. Because at the end of the day, we were trying to prove these state complexity bounds, and those were all about circuit depth. So I need a way of proving that some state cannot be generated by low depth circuits. I sort of need the hammer, and then I'm going to try to find a Hamiltonian whose all the states have this property. Right? And so here's how we do that. So here's a very simple fact. If I have a depth T circuit, then there's a corresponding local Hamiltonian. And it's not local in the exact same sense, it's 2 to the T local. So if T is a constant like 5, this is a 32 local Hamiltonian, for example. And this Hamiltonian has a very unique ground state, which is just the circuit applied to the state. So for every low depth state, there's a corresponding Hamiltonian that you should keep in mind. And it has a very simple spectral gap, it's just 1. The reason its spectral gap is 1 is because it's just a rotation of a simple Hamiltonian, and we know the circuit gap of that, spectral gap of that. And you can just prove this by induction. You just sort of say, okay, every time I have the depth, the locality just doubles and the spectral gap stays the same. Not too hard. Okay, that's fact one. Fact two is very simple. It says, let me consider a set of m points. And the property is that these are points in the Boolean hypercube. So, and the property is that they're far apart. They're L far apart. So that's just the notion of Hamming distance. Just says the number of bits you'd have to flip to get from x1 to x2. That's just the notion of Hamming distance. They're L bits apart in Hamming distance. And then what you can get is that the state psi, any state psi which is supported on these bits, it cannot be the unique ground state of an L local Hamiltonian. Just a fact. How do you do this? Well, the keyword here is going to be unique. That's all I want to show. So all I need to do that is to show that if it was the ground state of a local Hamiltonian, then there's some other state that's different. So what I'll do is I'll take psi prime, which is negative alpha 1 x1 plus the same weights on the other direction. I just flip the sign on the alpha 1, right? And you could just pick the first alpha that's non-zero, right? Okay. And then for any L local Hamiltonian term, let's notice that the energy of psi h psi can just be expressed by this, quadratic form. But then I just get that it's alpha j squared, right? Norm squared. So if there was a sign flip on that first alpha 1, it's lost here. So the energy is the exact same with psi prime. Okay, so I have the two states have the same energy, but as this holds for every inside local Hamiltonian term, for the sum of the terms by linearity, it's the same, so I have non-uniqueness. Okay, very simple. So it just says I have far apart points, it's not the unique ground state. Now I'm going to claim a corollary, which is that if I have this property, then it's not the output of a log L depth circuit. And how am I going to do this? Well, I'm going to put those two facts together, right? The first fact said what? It said that every depth T circuit generates a 2 to the T local Hamiltonian, right? But this says that I cannot be the ground state of an L local Hamiltonian. So put those two together and you just get 2 to the T equals L, flip it back, and you're going to get the exact result, the corollary, which is that it's not the output of a log L depth circuit. So it says something following, which is that if I was to take my quantum state, I was to measure it in the standard basis and just get a probability distribution. And the probability distribution looks like a bunch of disjoint points. Then that state is complex in the sense that there's this circuit depth lower bound. It's a very simple property. And it's not too much to actually go a little further and say that even if I had just these subsets, and I had that the state was supported on this subset, but I had the supports were far apart. So even if it wasn't just some points, but I had sort of a blocky, more nearsighted perspective, as long as I had the distance between them being L, I still get this log L lower bound. And we call this sort of distribution a well-spread distribution. So now we have a hammer, which is well-spread distributions. Whenever you have a well-spread distribution, you have a circuit depth lower bound. So what's there left to do to try to prove NLTS is just to find a Hamiltonian for which all the low energy states induce well-spread distributions. If you get that, then you're done. Okay. And let me say something a little bit further. It takes a little bit more work, but it's morally the same, which is why I won't, say the proof, which is that in the previous thing, I had that, the total mass was supported on these regions. But in fact, that's even overkill. You don't even need that. As long as you can get, there's some constant mu mass on the region. So you just have two regions, S1, S2. And when you measure and you get the statistics that you get mass on S1 with some probability and mass on S2 with some probability mu, then you get a lower bound. And it scales with the mu in there. So that's good. For some technical reasons, you get this L squared over N, but if L is, bigger than root N, then this is sort of still up to log factors just as good, right? Excuse me, up to constants just as good. Okay, so really, we're just looking for distributions that are well spread in the in the most granular perspective, just two kind of big blotches that are far apart. All right, so where should we find well spread distributions? Well, this is where the coding comes back in. Yeah.
I have a question. What does well-spread distribution mean physically?
For the state?
Yeah.
It just means that when you take the state and you measure in the standard basis, there's a corresponding probability distribution. Right?
No, I mean like what does it say about the entanglement? What does it say about the property of the state?
So it says exactly that this circuit depth lower bound, right? It says that if you were to try to generate that entanglement, your circuit would have to have depth like log n. So maybe some examples of well-spread distributions are useful. So we'll see that codes generate well-spread distributions, or like the cat state generates a well-spread distribution. So the cat state is the state which has half of its mass on 0 to the n and the other half on 1 to the n, right? So that's like global entanglement, effectively.
So what you're looking for is global entanglement.
Right, but you sort of want some leash on the global entanglement, and this gives you a way of getting a sort of a better handle on that global entanglement. Any other questions? Okay. All right, so where were we? We were trying to find these sort of well-spread distributions, and we wanted to find Hamiltonian systems for which all the low energy states induce well-spread distributions. So here's where we're going to go with this. So with error correcting codes, there's a nice picture. Pavel had a very similar picture in his talk, which is that you should think of a classical error correction code as a bunch of points that are spread out. They're spread out in the sense that the Hamming distance between any 2 points scales with n. That's like a good code. It really is the distance d, but for good codes, d scales with n. So it's the omega of n right there. And this is what the exact solutions look like for error correcting code. But what we actually care about is not only the exact solutions, but all the approximate solutions. Because remember, the whole idea of this whole thing started off by trying to understand the complexity of approximate solutions. So if I'm going to talk about codes, let me talk about approximate codes. And the nice idea is that if I'm going to look at the approximate solutions for a code, well, what is that going to look like? Well, first, it has to include some bubbling out around the actual code words. Because if I switch a few bits of the code, I'm not going to change the number of terms I satisfy. So I change just a bit or two of the code, I won't actually change, the number of checks I violate by that much. And I can actually even extend this all the way to my radius is like epsilon n. But the question is this all of them? This is not actually all of them, because what you actually get is that there are actually all these other bubbles that actually also show up. And the nice thing is that for good codes with high probability, you get that all the distances between all the clusters scales like linearly in n. This property is sometimes called the overlap gap property, or OGP, and it's sort of the property of what the low energy landscape looks like for a classical constraint satisfaction problem or a classical Hamiltonian. Okay, so this looks really good, right? Because I can sort of see what I wanted, which is that all the regions have distance scaling like n between them. And if I could just imagine, like I can just like group some of these purple clusters into my S1 and the other into S2, and I can just show that my quantum state has mass on both of them, then I'm done. Like you almost feel like you can almost taste the answer, right? Except there's one key problem, which is that if there did exist a low energy state which was supported exclusively on the purple regions, right? Then there exists another state, let's call it phi, with the same energy that's supported on a unique purple region. And this is exactly the same argument that we did previously in our fact 2. So we'll do it one more time, which is just like, let's consider that state psi. We're just going to do psi prime in the exact same way. I'm just going to do the negative alpha 1 flip trick. And I'm going to get that the energies will be the same. And now I get that psi and psi prime have the same energy. And so then roughly speaking, the difference between them, which is supported only on one of them, should have about the same energy. There's a slight bit more technicality there about eigenvectors and not eigenvectors, but let's keep it simple. And this is sort of the intuition, right? That somehow if your distribution is really, if your state's really spread out, you wanted to prove circuit depth lower bounds for some state. But in trying to do that, in trying to prove circuit depth lower bounds for one particular state, you ended up finding a different state for which you can't prove circuit depth lower bounds by the same technique. And the worst part was that second state also happened to have low energy. So you seem to have like come back and you're sort of stuck. So here's what we can do though, right? So let me just spell it out, right? You find this apparent contradiction. So here's where you do something truly quantum, right? So far, this previous picture was just with the classical code. And we sort of know that the classical code is not going to give us complex quantum entanglement by itself. We have to do something quantum. And to do that, we need sort of this notion of multiple bases for the rescue, which is that there's this very simple uncertainty lemma, right, in quantum mechanics, that if you're really certain in one basis, your measurement, then you're very uncertain in the other basis. Right? We know this like for just one bit, like measuring in the standard basis versus Hadamard basis, you have the uncertainty principle. But you can actually make an n-qubit sort of analog of this. The right picture to have is something like this. A small s in the z basis, if your measurement is concentrated in a small s in one picture, it has to have a large t in the other picture. And really, like the only time when you have like a really small s and like actually fit this way is when s corresponds to a linear subspace and then t corresponds to the orthogonal linear subspace. If s is sort of a random set of points, then t will also be random. But that aside, that when you have like a small linear space s, then the other t is big. You can formalize this in the following way, that like the amount of probability mass you put on t is bounded by like this equation in terms of the mass you put on s, but the picture is better than the formula. Okay, so here's where we go, which is our big NLTS intuition, which is actually first implicit in a paper of Lior Eldar and Aram Harrow, which is you want to show that the low energy states, not that the distribution is necessarily well spread when you measure just the X picture or just the Z picture, you want to prove it's OR. That's all you need is the OR. That in some basis, if you measured, you'd get out a well spread distribution. And that induces your complexity. So one way to look at this is that if you think of like the simplest example of an error correcting code, like a toric code, if you think about a toric code, what you have is that you measure the toric code in the standard basis, say, you'll get out 4 different clusters of measurements. The first cluster sort of corresponds to what we might call trivial loops. The other cluster corresponds to what are like non-trivial loops around it. And then the other 2 clusters, one corresponds to non-trivial loops in the other direction, and the ones corresponding to both. And I get these clusters are nicely spread out, root n spread out. So what I'm going to get with just like this toric code is I think of a toric code as complex entanglement. Right? I can prove that exact solutions to toric codes actually have this log n depth lower bound. The reason I get that is that I can't prove this well spreadness in this standard basis because I might just get all the states that correspond to loops that are trivial. The reason that this is sort of like these classes even have notions, right? This class is the measurements you get if you're encoding logical 0 and logical 0, the 2 qubits that you're encoding in your toric code. Each of these classes actually corresponds to some logical basis. What you're going to have, though, in order to get this uncertainty, is that there's a exactly identical picture in the Z perspective. Right? The toric code is equivalent in X and Z. So what I get is that if I was to look at it in either the Z basis or the X basis, I will find that well spreadness. And that's the key idea, is that the measurement cannot be concentrated in the Z basis, then it would be concentrated in the X basis. That's because to be concentrated, like imagine you're concentrated all on this one picture. Then if I measure in the Z basis, I'm totally uncertain, right, in both of these things. So the Z basis, I'm sort of uniform over all of these. So that's the key idea, is that somehow you have to use both bases. And so for that, what we do is we look at high rate, high distance error correcting codes, quantum error correcting codes, which give you this exact property that either the X basis or the Z basis measurement is going to be well spread. And the degeneracy, the rate helps you with like the size of these balls, although there was a recent result by Golowich and Kaufman on how to remove this degeneracy necessity and the distance you need for sort of the distance between them. Let me not say too much about the expansion. Okay. So that's sort of the idea, is that we saw that if you have this X and Z basis perspective, you got everything you needed. Where do we go from here? So let me talk about trying to construct local Hamiltonians, which are simultaneously NLTS. They have complex entanglement and are NP hard. So to start off with, let me point a failure of our construction, which is that it's a stabilizer Hamiltonian. meaning that the ground states can be described through the stabilizer formalism. So although we can prove state NP lower bounds in terms of circuit depth, in another perspective, the state NP in terms of the stabilizer thing, there exists a very simple state NP description of these states. So it's not going to, they're not the end all, right? So we can ask a question of, are there families of Hamiltonians where all the low energy states cannot be generated by low depth circuits and it's NP hard to decide the minimum eigenvalue? So here's an idea. Well, you just take a Hamiltonian C and you want to find a Hamiltonian whose ground state is proportional to the uniform superposition over the solutions to the CSP. You pick a CSPC and you say, I want this to be my ground state. I want this to be included in there because that thing is going to be well spread. So it's going to look something like this. I want the solutions to look like this. I'm just going to reuse the same pictures again and again because they really sort of hark on the same point. The problem, though, is unless this Hamiltonian was L local, where L is the distance between the points, then if the ground state was this superposition over states, even with phases, then any single point would also be a solution, right? And then your Hamiltonian really is just the classical CSP.
How does this make the Hamiltonian MP hard to decide? I mean, I know that it is already a yes instant CSP.
Oh, yeah, like where is the complexity?
Yeah.
So the first part is just about the low energy states of it, and the second one is about whether it was violated or not. So even if it was violated, you could imagine proving that all the low energy states are low.
Right.
Yeah.
Oh.
Okay. Okay, so what we need then is, you might say, okay, well, Chinmay, the real reason all this failed is because you didn't do anything in the bulk, right? You had mass on all these points and they're all really far apart. Like the lesson you should have taught, the lesson sort of throughout the talk so far is that, you can't have mass spread out so far apart from each other. That's just not what local Hamiltonian ground states or low energy states look like. So you might say, let me try to construct a state whose ground state is not exactly that. It sort of has a decay. So it has the most mass on the solutions, but then as strings violate more and more terms, so like it has a delta to the violation decay as you go further apart. This was initially suggested by Anshu and Breuckmann. Sorry, that N should be a B. And then another recent paper on overlap gap property. But the problem, again, is that this sort of decay between solutions, you can actually even express that there exists a Hamiltonian who has this as its unique ground state. The problem is that this decay just decays too much, right? Between the two peaks of solutions and the mass, there's very little mass that goes on in between. There's just too much bulk here to overcome these peaks. And what you get is the following problem, is that there exists a state which is not well spread. So well spreadness was the way we were going to prove our complexity and start to argue. But the problem is that I could just take whatever this state psi is and I can prune it in some radius around one of the peaks. And the idea was there was so little mass on this bulk around here that this pruning really didn't change the energy that much with respect to the Hamiltonian. And I got a state which was very simple. And this state actually sort of looks like just Gaussian noise around that peak. So it kind of seems to be a very simple classical state. And the lesson here is that this Hamiltonian that sort of corresponds to the CSP was defined too much in one basis. So I tried a lot over the last year to sort of rectify this and try to create a Hamiltonian which was not that much defined in one basis and sort of meddle with this picture. But I don't know how to do it yet. And sort of one question I have, for anyone interested in pursuing this more is try to figure out how to get around this barrier, how to encode your classical computation in these Hamiltonians with entanglement, and you have to sort of get around this one basis perspective. You need your Hamiltonian to really be some like X and Z terms. Maybe for the interest of time, I'm not going to talk about this connection to quantum money and lightning, although feel free to ask me about it later. But what you might ask is an intermediate problem. Next step is, can you find two NP problems, C1, C2? And can you construct a Hamiltonian whose ground states have the following measurement statistics? You measure in the Z basis, you get those clusters, in the X basis, you get those clusters. But the idea is that each cluster sort of corresponds to a solution to one of the NP problems. So in the Z basis, corresponds to solutions to C1. In the X basis, it corresponds to solution to C2. C1 could equal C2. That's not really the big deal. It's just, can you get sort of measurement statistics that look complex in both bases? Because if you can do this, then that's really the complex entanglement with the hardness, right? You sort of have the superposition, because you can't be too concentrated in one of these pictures, because then you'll be violating the other problem and so forth. I don't know if this is true. It seems hard, because it seems like the only time you get this sort of structure in both pictures is when the solution spaces look linear, and then you worry the problem gets a little easy, but I can't formally prove that this is impossible. Right, and the whole idea is this hardness that you really want the complexity, the entropy coming from the two different measurements. Okay, maybe introducing computational hardness is not the right goal. Maybe we go back and say, let's talk about stronger state complexity lower bounds. And for that, let me propose another class of problems, which sort of takes the apex of the stabilizer problem and the circuit lower bound and combines them in the right way. So I called this, I called these trivially rotated stabilizer states. So the idea was that constant depth quantum circuits is just one form of a state NP proof. And here's another form of state NP objects that I don't know how to prove lower bounds against. And they're the following notion. You start off with all zeros. It's the set of states that can be formed in the following way. You start off with all zeros. You apply any Clifford circuit. Clifford circuits are just the ones that move through all the stabilizer states. Apply whatever Clifford circuit you want, and then you apply a constant depth circuit at the end. So why might you consider something like this? Well, think of it like building your house. You want to first put all the beams and all the reinforcement in and the complex global entanglement. You can do all that with your Clifford circuit. You can produce long-range entanglement. And then you want to sort of apply the roof tiles and the shingling and all the like final edges that bring you to the thing. Because what happens is the Clifford circuits are kind of coarse. They don't really let you get as close as you want. You'll still get like some constant angles from the states you might desire. But maybe then your constant depth circuit on top can sort of fix that and help you like sort of, simplify all the edges. So I call these trivially rotated stabilizer states. Trivially rotated being this is the trivial rotation and this is the stabilizer state. And there's a conjecture which you could ask, which is, to prove lower bounds against this type of state NP object. And the work of Nolan and his co-authors at Maryland is sort of the and. It's proving that there are states for which have no Clifford circuit and the constant depth circuit, but they're sort of two different pictures. They're not stacked one on top of the other. This seems like the hard one to do. And I'm not really certain what the techniques might look like for that. There's also this other conjecture about state MA lower bounds, which I won't exactly mention. Okay, but maybe go back and try to prove that quantum PCPs are MA hard or BQP hard. And we actually heard a little bit about this from Anurag's talk on these new constructions of local Hamiltonians embedding computation. And that was the sort of a different circuit to Hamiltonian construction based on measurement-based teleportation. But their current proof only guarantees really the complexity bounds for low states, energy states of a combinatorial nature. What you really want to do for the quantum PCP is you want to prove complexity for all low energy states. So that's the missing step right there. And the best you could get to is sort of, even if you were able to prove replace from combinatorial to all states, the best you'll get to is like a promise gap that scales like 1 over log n, which is better than what we can do right now, but it's not the like constant epsilon that you might want to get for quantum PCPs. But I still think this is a really remarkable partial progress. And it's kind of interesting because you first adjust your gates and circuitry to sort of do the hard work of the PCP amplification. That's maybe the moral takeaway, is that the fault tolerance that Anurag talked about in the talk that's necessary in like the in the setup, maybe that's really just doing all the amplification a priori. I haven't fully grasped this idea yet. Lastly, a lot of people ask me, to say, Chinmay, what if you have these like really good quantum codes, why can't you just get to the quantum PCP right away? Like classical PCP was not too far after like understanding of good classical codes. And here's the real issue, which is it's a folklore idea about quantum error correcting code that if your code has distance d, then the reduced density matrices of that code of distance less than d are invariants of the encoded state. Like morally, there's no information contained in small regions of error correcting code. Like this is the fundamental problem with error correction in the quantum setting, and it was what makes like all the logical gates and all the manipulating information inside error correcting code so hard, is that the information is inherently spread out. In order to correct the errors, you had to spread the information out. And there's a very simple proof to see that, and I'd like to just go through it. It comes from two ideas. One is just no cloning, and the other one's what is the definition of error correction. So no cloning just says this map doesn't exist. Here's the quantum error correction. Imagine you had an encoded state. Imagine some erasure error occurred, so you lost these red qubits. Okay, so then you got this state without those red qubits, just disappeared. But imagine instead those red qubits were not really lost. You just kept them to the side, just took them out, right? Basically the same thing. But here's the problem. If you correct that error, you recovered those red qubits. So now I got from this state to this state, and I seemingly cloned the red area. The resolution for error correction is that the value that was expressed on those red qubits by themselves was something you could have come up with all on your own. You could have gone from here to here all by yourself, which is just to create that red state by yourself. It didn't depend on what state was being encoded. So this is the idea that like the local regions don't contain any information. This is how you can formally show it. So that's the problem, because at the highest level of generality, right, the classical PCP is just really like wrapping the solution in a really nice, elegant code. Just take a very good code that's locally testable, has all your favorite properties, you wrap the solution in it. But the problem is that if you did that with a quantum PCP, even if you had like your best QLTC, which we don't know if it exists, you wrap it, the local Hamiltonian that verifies it must have locality L being at least D due to this local indistinguishability property. So either you weren't using a very good code, you're using a constant locality code, and then you ask, what's the point of using the code in the first place? Or your Hamiltonian has really large locality. So the takeaway of these last slides is that just having error correction is not enough to sort of make this leap to quantum PCPs. It seemingly seems like a part of the picture because it's one way that we know to prove complex entanglement. And we certainly feel like we need some of those notions of error correction in there. But by itself, it's just not enough, right? You somehow have to do some if it's going to work out, it might look like some complex iteration of some amount of error correction, then some Hamiltonian transformation, then error correction, transformation, error correction. And that, mathematically, that's far more interesting than just saying, boom, I have this object and I wrap everything up and it sort of works out. So with that, I'll leave you hopefully a little confused and a little excited about some open questions. And yeah, thank you.